So let's talk a little Pythagorean theorem. So the purpose of this video is to help you consolidate maybe some of the information you have found so far in your little activity today, but also maybe reveal some stuff you didn't quite get to that's an extension. If you're hearing some background noise, it's because I'm in the hallway right now, especially if you're in a 3A class, like I'm literally outside right now. I'm doing this work, and so if you hear people walking by or screaming or something, know that physics is um, doing something with a bowling ball down there, so probably get a little loud. So if it turns out you can't hear this video really well, tell me and I'll try to reshoot some of the audio. So anyway, let's get to the actual work here. So there's quite a bit of things we need to figure out. Like the way this kind of came together is that we noticed while grading some of your work over the last couple topics, the Pythagorean theorem was consistently missed. Not by everyone, of course, but enough that we think is a problem. We also know that since you probably skipped 8th grade math, you didn't get the full lessoning on Pythagorean theorem as some of your peers, and it's fair that you should know this stuff too. So here's what we think you have to know. So let's talk about this first. What does it actually mean to solve a triangle? Now, you may not use this terminology today, but this terminology is going to be really, really important to your future. And so it's important that we're on the same page, at least for this vocabulary. So in the context of triangles, when I ask you to solve a triangle, what it actually means to do is to tell me everything that's missing. So solving a triangle means find all missing pieces. Okay. And so, so if I have this triangle, what that actually means is there are very specific things I want you to be able to find, namely 3 angles, which I'm going to designate alpha, beta, and gamma. Remember, those are just angle markings. And then 3 side lengths, which correspond to A, B, and C. And so there are 6 pieces of information that you actually have to find if you actually want to find, solve a triangle. And so the interesting thing that we're going to examine over and over again is how do you do that? What are techniques that you have to solve this triangle, okay? So that's really all there is to solving a triangle. Let's talk about what is the Pythagorean theorem, how is it used to solve a triangle. Now this is going to be mostly review, but it's a good review, so it's okay that we're going through this in notes. And so the first thing you should know is Pythagorean theorem only applies to right triangles. This is, again, probably not new, but it's good to have it as a review. And so when you look at a right triangle, you can see that there are 5 other pieces of information involved, but Pythagorean theorem focuses on the side lengths. And so we have 2 sides. We have a short side and a long side, more often than not. There is a case where everything is actually the same, but we usually designate one side an A and one side a B. Now, it doesn't really matter which. In fact, it doesn't really matter what variables we use. And so even though traditionally we use A squared, B squared, C squared, I'm going to use something else. I'm going to call this side X, I'm going to call this side Y, and this side Z. And so the Pythagorean theorem turns out to be this relationship, x squared plus y squared equals z squared. Now here's where some people start to have a departure from logic. And I don't want you guys to do that, so let's think really hard about this. If you look at this Pythagorean theorem, some things should start to become really obvious. The biggest one is that whatever this value is, of course called the hypotenuse, is going to be the biggest value. Now that's not just by rule, it has to do with logic. We have 2 things that are being added together to get z, or in this case z squared. So it makes sense that z should always be the biggest side. Now there's a bigger reason for that. There's something we'll talk about in class called the hinge theorem. The hinge theorem talks about how big an angle is versus the side that it defines. And so you can also look at the hypotenuse as being the biggest side because it's across from the biggest angle, which is the right angle. Which also implies then the smallest angle is going to help define the smallest side. And so the way I have this picture drawn, if it turns out that, let's say, the angle I'm currently marking is the smallest side, that means x will be the smallest side. But in terms of actually solving using the Pythagorean theorem, it doesn't matter what. And so this is a relationship. You usually see as a squared b squared equals c squared, but here I just have it as x, y, and z. Now how this is used is actually purely in algebra. And so the idea here is that you need 2 pieces. Okay. Now, algebraically speaking, this should, again, not be a surprise. The reason being is that you have 1 equation and 3 unknowns, x, y, and z. So if you have 2 of those pieces, you can use those 2 pieces and this relationship to solve for the third. Okay. Now, this is a very kind of thing you should note in your, an important thing you should note in your notes, is the Pythagorean theorem is only useful to us if we have 2 of the 3 side lengths. And so another way to say that is that this does not truly solve a triangle. Because you can't solve angles, there's nothing here about how the angles relate. If you don't know your angles to begin with, this is no bueno, it's no good. But you can use it to solve solve the third side. And so we can make a little note here. Truthfully, wow, look at that handwriting. I'm very distracted by these bowling balls that are happening down the hall from me. So let me change colors as well. So we're going to make this note. Truthfully, the Pythagorean theorem cannot. Okay, so truthfully, the Pythagorean can only partially, which is what that poorly written word is. Let me change that. Partially. It can only partially solve a triangle because it cannot find angles. It can only solve side lengths. So when we talk about the common traps and mistakes, like you guys are currently right now are going to be in class discovering some of these like traps and mistakes that you can make while solving the Pythagorean theorem. And so you can probably fill this with more things than I can possibly give you, but I did want to highlight two things, two common traps that people fall into in solving the Pythagorean theorem and how to avoid them. The number one trap, by far the most common trap, is choosing the wrong pieces. Okay, now what I mean by choosing the wrong pieces is that if you observe the Pythagorean theorem as being related to a triangle, let me actually draw this a little more obviously. Okay. You have, of course, three sides, but there's always one longest side. That's the designation as a hypotenuse, of course. And so here I'm going to use T, V, and Y. Okay, why am I using it? Because again, the letters don't matter. And so in all cases, it's always going to be one side squared plus the other side squared is equal to y squared. It has to be in this order again because y must be the biggest side. You can't have two things add to a third thing and that thing be smaller than the components. That's not how addition works. And so the way this kind of usually presents itself is an example as follows. And so let's say I have this triangle, and I know it's a right triangle, of course. I know this side is 3, this side is 5, but I want to find x. The mistake, and again, let me highlight this as a mistake, is that someone will blindly, without thinking, take this to be 3 squared plus 5 squared is equal to x squared. Now, this is wrong on a couple different levels. The biggest reason being that whenever you find the value for x, it's going to be bigger than 5. It has to because you're adding 3 squared to 5 squared to get x squared. And so like this, let's make a little annotation here. This will end up being bigger than 5. And of course, that's impossible. Okay, and we probably see this mistake, 10, 15 times a week, which is just because I think, and this is just my opinion, because you're not really thinking about like which side should end up being biggest. And if you kind of keep that conception in mind, like the hypotenuse must always be bigger, you know that this is not actually what you should be doing. The correct answer would be 3 squared plus x squared equals 5 squared. And so like the correct version should be 3 squared plus x squared equals 5 squared, which means you're going to have to do a little algebra on the back end to solve it, but that's totally something you can do. So just be aware this is one big mistake. Another big mistake that you can totally make when using Pythagorean theorem has to do with the algebra itself. And so let's look at example number 2. Okay, so let's say again we have this triangle and you're trying to solve it. And let's choose, let's make this 6 squared, let's make it 6. Let's make it 8, and let's say you're solving for x. Okay, and so this is not a tricky one because like you are going to take the two sides and component them together, and so we'll have 6 squared plus 8 squared is equal to x squared. Now here's where the mistake comes in. So let's line this out. Mistake. The mistake comes in when you try to do your next step, and so we see this a little less often, but it's totally as insidious. That when we take the square rooting step, this will somehow and magically become 6 plus 8 equals x. And so like the note we'll make here is that the mistake is that you might think that the square root cancels the squares. Okay, that word's cancels. Let me try it again. It's getting more distracting down there. They're really going crazy, these bowling balls. Okay, now it doesn't, so it is true that a square root does cancel a square. The reason why it doesn't happen in this case is because of that addition sign. The addition sign makes this a two-termed expression. Two terms meaning that the two things being added and subtracted together. So that does not work in this particular case. If you think back to your Algebra 1 class, you guys talked about the difference. I'm going to put the reason why over here. You guys talked about the difference between taking something like this and squaring it versus taking something like this and squaring it. Let me write a little versus sign here and change colors. 3x and squaring it. In the bottom case, you're just basically multiplying 3x times 3x. There are like two of them, 3x times 3x like this. And so this will end up becoming 3 squared because there are two of them being multiplied by x. And there's two of them. And again, the big thing here is because multiplication. On the top, though, that's not how it works at all. This will actually be x plus 3 times x plus 3, meaning that you're going to have to do like a double distribution problem, and this will end up being x squared plus 6x plus 9. And so the difference between addition and multiplication presents itself on the difference between how squares and square roots interact. And so it's totally true on the bottom that if I were to take the square root of this, it's the same as taking the square root of this, or actually individually taking the square root, which means that it actually would cancel right back to 3x. That's not the case here. If I try to take the square root of the whole thing, this is not the same as taking the square root of each individual part. And so it's not true that it's like x squared plus the square root of 6x plus the square root of 9. It's just not going to get you back to x plus 3. And so it does not work, and it'd be good to put that in your head as one of the things that you should never ever do when you're dealing with Pythagorean theorem. Okay? Now we have this kind of cool thing called the inverse of the Pythagorean theorem. And so if you think about what the Pythagorean theorem says, it says, like if you have a right triangle, let me actually change this up a little bit. So let me just use symbols actually, that might be better. So the converse says, if you have a right triangle, and of course a right triangle is going to be any triangle that you have a right angle in, then, which I'll use symbols, then is true. I have a rough time trying to move the screen. Then it's true that, and I'll go back to common things here, a squared plus b squared equals c squared, where a and b are defined to be like your two sides and c is your hypotenuse. Now, I mentioned several times it doesn't matter what order a and b come in, which should make some sense because we're adding, and of course addition doesn't matter. And so if we're dealing with a converse, it actually is just a reversal of this. So like the converse, so just the opposite. And so let me just do some cut and pasting here. So it says if you have a situation, and you may not know exactly what kind of triangle you have, but you do have a situation where a squared plus b squared equals c squared, then then you have a right triangle. Sorry for the stilted speech there, guys. I'm trying to do more than one thing. Sometimes my brain can't process. Okay, and so the converse goes actually just back from that. So if you have a right triangle, then a squared b squared equals c squared. If you don't know what kind of triangle you have, but a squared b squared equals c squared, then you're going to have a right triangle. Now the reason why that's important. Now let me move these common tricks down a little bit. Man, that class is loud. Okay. Now the reason this is important is because you can actually tell what kind of triangle you have because of this implication. Because the converse happens to exist, we can then use that to our advantage. It's like, for example, let's just say I have this triangle, and the side lengths are 6, 8, and 10. Well, applying the converse, that means we can try this out. 6 squared plus 8 squared, which is going to be, let's see, 36, let me change colors. That's going to be 36 plus 64. Which if I simplify that one step is going to be 100. And let's say I compare that against 10 squared. which 10 squared, 10 times 10 is going to be 100, and they're the same, that means I'm meeting the first part of the condition, which implies that 6, 8, 10 is a right triangle. Okay, and so we can also use it to test if something's not a right triangle. So by more implication, again, let's go to examples here. Let's say I choose two of the same numbers again, 6 and 8, and then 10 again. Well, fast forwarding, we know that 6 and 8 is going to be 36 plus 64. Oh no, sorry, let's not pick 10. I don't know why I did that twice. I'm changing that to 9. All right. So we know that's going to be 100. Now 9 squared is going to be 81. Now, of course, these are not equal, but the more important part is what can I tell because of it? Well, think about this for a second. We have this triangle, but the hypotenuse, which should have been 10, is too short. And so we should have had a triangle that looks like this, but instead we have a triangle whose hypotenuse was not big enough. Let me increase the size just slightly. Okay, so it came to like here. It should have been 10, but it's actually 9. Well, the important thing is what happens as a result of this. And so to even make a triangle, we have to connect these pieces. But since the hypotenuse was too short by a unit, the only way to make this a triangle is to swing this side in and make it here instead. And so instead of this angle being right like it should have, it's actually going to decrease in size, which means, by implication, that this is an acute triangle. And so the application of the Pythagorean theorem's converse is actually more interesting. This Pythagorean theorem, we can actually determine triangle size. And so then, by the same kind of logic, if you had a triangle with like 6, 8, 11, this would be obtuse, because the exact opposite thing would happen. Your hypotenuse would be too long. Okay. So let's get rid of this for a second. All right. So let's talk about some tricks that kind of evolve from the Pythagorean theorem and its converse. There's two really important ones that are worth talking about, and so let's see if we can do this on the fly. So let's consider, for example, a equilateral triangle. It doesn't really matter what the sides are. It doesn't really matter what the sides happen to be, so I'm just going to call them x, and keep in mind that this is going to be an equilateral triangle. So without knowing why, let's just go ahead and cut this in half. Now, something to note right off the bat, since it is equilateral and 180 degrees to find a circle, that these must be 60 degrees apiece. Okay, so when we execute this cut down the middle, a couple things happen. Now, the right-hand angle stays 60. This would, of course, be a 90, but more importantly, this would become a 30-degree triangle. Okay? Now, even though it doesn't seem like it, I can still find the sides of this triangle. One by implication, the second by Pythagorean theorem. And so if this bottom side length used to be x, now we know it's going to be 2x. I'm sorry, 1/2 x. Okay? If that's 1/2 x, now the question we should occupy ourselves with is, what's the length here? What's the question mark? Well, it is a right triangle, and even though it's a little bit weird to do it this way, we can use Pythagorean theorem to define that side. And so if we consider a squared plus b squared equals c squared, a can be either one of the side lengths, so I'll take the bottom to be 1/2 x. And we're going to square this guy. Let's go color code just so we see where everything is coming from. Okay, that's 1/2 x. The b value, well, that's just going to be a question mark. I don't know what it's going to be, but I'm going to square it. And then c squared is going to be, in this case, x squared. So if I'm interested in finding out what this unknown length is, the altitude that drops straight down to cut my triangle, I just have to solve this guy. And so here, in our solving, we're going to square the fraction, making it 4th x, or squared. Okay, we have the question mark. Squared, and of course, this will be equal to x squared. So now we just have to continue our solving. Okay. So it looks like we're going to subtract 1/4 x here. Of course, subtract it from this side, and that should be x squared, excuse me. So solving this out, we end up with a question mark squared is equal to, well, if I have a whole and take away a quarter, that's going to be equal to 3/4 x squared. Okay? We're pretty close to the end here. All we have to do is imply a square root. And so that means the question mark is exactly equal to 3/4 squared. Okay? And so if I square the top and bottom separately, that'd be square root of 3 over the square root of 4. Square root of 4, of course, is 2. And so this unknown side length is going to be precisely equal to square root of 3 over 2x. Okay? Now, that in itself doesn't seem like a useful result until we look at the sides piece by piece by piece. And so I'm going to redraw the triangle here. Okay? So here we have half of an x, here we have x, and here we have square root of 3 over 2x. Now, it's a little weird to have these fractions in here, but you know a little something about similarity. So I'm going to blow this up to a k factor of 2. And so, like, if I blow this up into its kind of final form, okay, looks like I need a little more room. Let's make this a little smaller. Okay, so to make that a little smaller, I'm going to blow this up by a k factor of 2, which means I'm doubling all my side lengths. That means this will be 2x, this will be x, and this will be times 2 will be square root of 3 times x. Now, I know it doesn't seem like a really amazing prospect, but this is actually a really cool result. Now, this only works because of the type of triangle we chose off the bat, and if you recall, that was a 30, 60, 90 triangle. This would be the 30 because it was 60 that we cut in half. This will be the 60 because it's the angle we didn't cut in half. Of course, the 90 because of the way we cut the triangles. We dropped right down the middle. And so what this implies is for a 30, 60, 90 triangle, this relationship will always be consistent. Which again, it doesn't seem like it's a really big deal, but it's actually a really cool thing. And so what that means is if I have a triangle that I know is 30, 60, 90, call this 60, call this 30, and all I knew was that this is 10. I can actually get the other two side lengths very, very quickly. Because if that's 10, that means the bottom, the smaller side, the one across from the 30, would have to be half of that because 10 is 2x, x would have to be 5. It also means in the other side length, the one that's straight up and down in this particular case, across from the 60-degree angle, would have to be 3 times x, so it would actually be 5 times square root of 3. So if you notice, without using Pythagorean theorem, just because I knew I had a 30, 60, 90 triangle and this relationship, I ended up with all 3 side lengths immediately, like it took me seconds. And so that's just a trick that evolves itself from the Pythagorean theorem. There's actually another one that's equally kind of cool. It's going to kind of evolve the same way that the other one did, by using the Pythagorean theorem kind of in a clever way. Okay, so let me create a little more room for ourselves. Alright, so let's divide this. Okay. And so the other cool one is if I have a special kind of triangle, but in this case it's an isosceles. And so I'm going to actually start with the right triangle, but I'm going to start with the right triangle that's 45, 45, 90, because if the side lengths are the same, it makes sense these angles are. Okay. And so again, we're going to use this as a general case. So let's suppose, just for a minute, that this side was x. Well, we immediately know, because of how triangles are formed, this side should be x. And so the only unknown side length is this guy, this question mark. But fear not, we have the Pythagorean theorem. So since we know a squared plus b squared, let's see. Okay. We know a squared plus b squared is going to equal hypotenuse, which is going to be c squared. So that's going to be question mark squared. B squared, let's just take it as an x, of course, square it. And then the other side, which should also be x, because it doesn't matter, we'll square it. We can just solve this in general. So we have x squared plus x squared will actually be a 2x squared. And now you can question mark squared. Okay. If we want to solve for x, we'll have to divide by 2. I'm sorry, we're solving for question mark, excuse me. So we're trying to get question mark by itself. We're trying to figure the hypotenuse. I'm sorry, I misspoke. So if I want to find the value of this question mark, I'm going to apply a square root. And since the left-hand side is actually multiplied, we can actually square root things separately. So square root of 2 times the square root of x squared. Well, square root of 2 is going to be the square root of 2. We can't do anything about that. What we can do is fix the square root of x squared, which square and a square root will, of course, just be x, which tells us our hypotenuse will always be square root of 2 times x. So again, we actually have kind of a neat result that we can take advantage of if we happen to have an isosceles or a 45, 45, 90 triangle. So to rewrite the relationship so hopefully it's a little more clear, if I do have a 45, 45, 90 triangle, okay, which means these two sides are going to be the same, x, x, and this will be, the hypotenuse will always be x times the square root of 2. And so like in a practical example, let's say, again, I have this 45, 45, 90 triangle, and all I know is that this side is 10. Well, extremely quickly, I know for a fact this side's got to be 10. That was pretty easy. But this side's just going to be 10 times the square root of 2, and it'll always be the case that this is also true. We can also work backwards. And so let's say we have another 45, 45, 90 triangle, isosceles, and all I know is that this side is 20. I'm using the same relationship but going backwards. I know that 20 is a result of the side length times the square root of 2. And so the side length x times the square root of 2 equals 20, which means that my side lengths x are going to be 20 divided by the square root of 2. Now, in this case, we had to do a little rationalizing, a little denominator work. But to get this by itself, we can just multiply by 1. You guys remember this from algebra. Multiply top and bottom by the square root of 2, which means my side lengths will be 20 times the square root of 2 over 2. Because square root of 2 and square root of 2 just make it 2, obviously, right? Which means I can then further, too much, which means I can further simplify the 20 and the 2 into a 10. And so these would just be 10 square roots of 2, and this will also be 10 times square root of 2, okay? Now, these last relationships are not something that it's vital that you know, but they're really neat tricks that really honestly helped me when I was going through math. Because I knew anytime I saw a 30, 60, 90 triangle, the side length relates this way, or I saw a 45, 45, 90, the side lengths relate in a certain way. And so what you really have here is one simple idea that evolved itself in many different ways. And so to solve a triangle, you could use Pythagorean theorem. Even though it can't fully solve it, it can at least tell you the three side lengths, as long as you have 2 of them. Okay. Avoid common mistakes, like picking the wrong pieces to go in the formula, or doing some kind of crazy made-up algebra. But if you have the Pythagorean theorem, that means you can also go backwards as a converse. That means you can tell what kind of triangle you're dealing with right away. And then an extension of the Pythagorean theorem comes in these really two nice 45, 45, 90 triangles and 30, 60, 90 triangle shortcuts. Okay? And so the only thing that's missing from these notes, if you choose to use them in the future, is your summary. And to remind you what I said in class and continue to say in class is that we're going to be more careful about what kind of notes you get to use on our test from this point forward. And so the thing that we want to see you do is, of course, read the notes. Then I want you to highlight or underline, which is what these two crazily written words are, highlight and underline, or underline, I should say, whatever your preference is. 5 words or phrases that you think are really important to answering the essential question. And the essential question, at least I try to answer in these notes, how can you solve a triangle with the Pythagorean theorem? What are common tips and tricks when doing so? So 5 words or phrases to help you do that, and then actually answer that question in your summary. And so I've been seeing some really subpar summaries. I don't want to see them anymore, guys. You're better than that, so act better than that. All right? So that does it for this video. There'll be more to come, but this is for the Pythagorean theorem. Thanks.